Today we're going to have the last class on steady state conduction in 1D and the concept of thermal resistance. So let's do a quick review of what we saw so far. So we saw an analogy between electricity and heat transfer that let us establish an electrical analogy of resistor and something very similar to Ohm's law. So now instead of having an electrical resistor, we're going to have a thermal resistance. And we define the resistance as the temperature, the temperature change for a given flux of a rate of heat, right? And we also define it per unit area with this horrible notation in which resistance per unit area means resistance times area. And we looked at the case of the wall, and we determined these results for the wall by solving the partial differential equation that we saw in our differential control volumes unit last week. Now, for the wall, it's so simple because it's steady state and it's 1D, and the answer was a straight line. And when we did all the calculations, we could establish that the resistance per unit area, the thermal resistance per unit area of a wall is thickness of the wall divided thermal conductivity of the wall. Now, this is a very simple thing, but we can build on top of this because we can say, okay, what if we have two walls, right? And that the equivalent of that is two resistors in series. And we can calculate that, and we can calculate the intermediate temperature. And all that is in the notes you have uploaded, and is in, and we discussed last class too. So that way we started with an example, say, let's have a wall that is built of brick and stucco. It's not the way we build the walls in Canada because it's not a good, awesome thermal insulation. Actually, you want fiberglass and other things to be parts of your wall when you have big temperature differences. But this wall was easy to start discussing. We say, let's say it's only brick and stucco, and we calculated the thermal resistance in this case is a resistor in series, and we saw that the resistance of the wall, the brick, was much bigger than the resistance of the stucco. And from there we got the concept of dominant resistance. In this case, the dominant resistance was the biggest resistance in the system because it was a series system. In the case of parallel resistors, is the smallest resistor, the one that is dominant. The definition of dominant is not which one is biggest or which one is smallest. The definition of dominant is the one that has the biggest influence on the overall resistance. However it is, if you have a very, very complex circuit, but one of the resistors conveys most of the final result, that resistor would be the dominant one, whether it's parallel, series, big or small, whatever it is. So we saw in this case, the brick was dominant, the stucco was secondary. What we then did was to look at convection, because convection also has an expression in which the heat transfer is proportional to the temperature difference between the surface and the fluid away from the surface. So this is cool because now we can establish a thermal resistance for convection. And in the case of thermal resistance per unit area is 1/H, right? For conduction used to be thickness divided thermal conductivity, now is 1/H. Now we can consider the case of a wall that has thermal conduction and convection on the surface, right? And then we looked at the case of our brick and stucco wall, and we accounted for the convection resistance inside, assuming natural convection at 10 watts per meter square Kelvin, and for forced convection because of the wind outside at 100 watts per meter square Kelvin. And what we saw is that the outside convection was so intense that it was almost as if we had no resistor there. But inside, we saw that for this particular problem, that the natural convection coefficient inside the thermal resistance of natural convection was comparable to the thermal resistance of the wall. So our wall, this brick and stucco wall, was actually better insulating than we thought, just because it has this layer of air surrounding it inside that acts as a little bit of an insulator. And the last thing we saw last class was, okay, given that we can assign a thermal resistance to conduction and we can assign a thermal resistance to convection, can we assign a thermal resistance to radiation? And for that, the answer is yes, but we need to cheat a little bit, because both convection and conduction have formulas in which the coefficient in the formula is more or less constant, and they're indeed more or less proportional, the heat transfer and the temperature difference. In radiation, it's not quite like that, because heat transfer goes with the fourth power of temperature. However, we had said that there is an radiation equivalent convection coefficient that is not for convection, right? It's for radiation, but it looks like convection. And we know how to calculate this coefficient. So this coefficient, which we know is not constant, to some extent doesn't vary so much in many cases. So let's assume it is constant, and we can write the thermal resistance of radiation as this last equation here at the bottom, as resistance of radiation, or as 1 over H radiation, the equivalent convection coefficient for radiation, that is this expression here. So now we can account for conduction pretty much exactly with the concept of resistance. We can account for convection pretty much exactly with the concept of thermal resistance, and we can account for radiation quite okay too. Perfect? No, but it's quite okay. So let's look at the case of a wall that has convection and radiation. We saw this last class too. And the wall has a thermal resistance to conduction, and we have it here. And then has some thermal resistance to radiation, to convection outside, which is here. So far, the same we have seen before. But in addition, we have a heat transfer by radiation that happens simultaneously with the convection. So this is a parallel circuit now. It goes by convection and at the same time goes out by radiation. It's not exactly parallel because convection goes with T infinity, which is the temperature of the fluid far from the wall, and radiation depends on the difference with temperature of the surroundings, which are not necessarily the same as the temperature of the fluid. So we have bifurcation and the heat goes these two ways. If we can say what is true in many cases, that the temperature of the surroundings is the same temperature of the fluid, only if we can say that, then this circuit becomes a true parallel circuit. And I can calculate the effective the equivalent resistance of this parallel circuit here. So, and here I have, how would you calculate this total resistance the resistance of parallel circuits is the reciprocal of the total resistance is the sum of the reciprocals. So the same way the total resistance in series was R total equals R1 plus R2, if those were in series, in a parallel circuit, we would have R total to the minus 1, the reciprocal, equals R1 to the minus 1 plus R2 to the minus 1, the sum of the reciprocals. This is what we see here. This is the equivalent resistance of the parallel system. All right, how about if now we go back to our stucco, brick and stucco wall, and we look at the equivalent circuit for heat transfer, accounting for conduction, accounting for convection, accounting for radiation, and accounting for the different materials involved in the wall. And this is the circuit we would have. What do we see in this circuit? Again, this looks like you're getting a degree in EE, right? But no, this is heat transfer. And this is what you need for heat exchangers. And this is what you need for understanding materials processing systems. This is what you need to design processing plants. So let's start in a systematic way. Let's not get intimidated by this. Let's not get too excited about it. Let's start by this part. We have this series part that is the resistance of conduction of the brick wall and the resistance of conduction of the stucco cover. So this part is what we started with. It's here. Then we have the heat transfer by convection, which we also saw is this part, this part here. This is the heat transfer by convection from one surface and the heat transfer by convection on the other surface. And in addition, now we have the heat transfer by radiation that happens from the same surface to the surroundings. Here we have one going out by radiation to the surroundings in the outside of the house. And here we have the resistance, thermal resistance of radiation that goes to the surroundings inside the house, the surroundings of the wall, which is inside the house. What are these four batteries here? This T infinity 2 is the temperature of the air outside the house. T infinity 1 is the temperature of the air inside the house. This was, we said, 20 degrees. We said this one was minus 10. This is the temperature of the surroundings, what the radiation sees. We talked in one example way earlier in the class that the surroundings at night could be as low as 0 Kelvin, right? Even if the air is at 20. In this example, I'm going to assume something else, but I'm going to discuss what these values of temperature of surroundings outside and temperature of surroundings inside are. I'm going to discuss in a second. What is the temperature of the outer surface of the wall is this point here. And what is the temperature of the inner surface of the wall is this point here. Right? So if they ask us, what is the temperature of the wall, given that the air inside is at 20 degrees? The temperature of the wall is not 20 degrees. Temperature of the wall is something lower than that. We calculated it, right? It's like 9 degrees, I think we got. I don't remember exactly, but it was more or less, give or take 10 degrees. What is the temperature outside? The fluid outside was at minus 10. And the temperature of the wall, I think, was more or less minus 9 because the convection here was very intense. Before we do any math, I'm using only our intuition. So if I were to assume that the temperature of the surroundings outside is more or less the same of the temperature of the fluid outside, I just want to assume that, right? Let's say the air outside is at minus 10 and what the wall sees might be trees at -10 too, right? My question to you, and I would like to see someone type in the chat, is if the resistance of heat transfer by radiation is increasing the heat losses or decreasing the heat losses. Because I consider radiation now, do I have more heat losses or less heat losses? I'd like to see somebody take a bet on this. No, the resistances are not the same, but the answer to this question is independent of the resistance. Okay, somebody suggested less. Okay, too bad we're not in the class, because I would like to hear why you think it's less. But the answer is more. I'll tell you why. This is the amount of resistance that was going out by convection. Resistance of radiation, whatever it is, can be small or can be big, just opens a new path for radiation, for heat to go. So that in a parallel circuit, having more resistors in parallel, essentially all they do is taking up more path for losing heat. Essentially, if you're trying to go from the university to your house, if they open new streets, you can only go faster because you have more choices, right? There are more ways to take cars. And this is what happens, right? If the road is longer, if instead of telling you, okay, your distance from the university to home now is twice as long, that would be like a serious case, and you would take longer to get home. But if I say, for the same distance, I give you more options, you can only go faster because there will be more traffic rerouted, you'll be better off. This is what's happening. So now let's look at the wall of a house, because there will be interesting considerations. One of the considerations I mentioned is, let's assume for this problem that what this wall sees is the same temperature of the fluid. For example, if the air out there is at more or less -10, the trees are more or less at -10, right? Okay, so I'm going to assume for this case that these two are the same, and this becomes a true parallel circuit. Now, let's look at radiation. Let's say that this room is very idealized and has just the 4 walls, ceiling, and floor, and they all have the same properties. So for a wall to lose heat by radiation, it can only lose heat by radiation to the other walls, because in this idealized room is all enclosed. If all the walls have the same temperature, then my losses by radiation inside are 0. And the reason is that the losses by radiation would be T of the surface minus T surrounding. And when the T surrounding is the same T of the surface, is one T to the 4 minus the same T to the 4. So there will be no losses by radiation inside, because all the temperature inside, in this idealized case, all the temperatures inside are the same. And if there is no temperature difference, there is no heat transfer by radiation. So this resistor here is the same as not having it. We can forget about it because there is no heat transfer going on by radiation. These two became a proper parallel path. So this circuit here, and again, we're talking about walls in a house. We're not talking about electrical engineering. The reason we make this electrical looking diagram is because the calculation of heat losses in a house, if we don't do it this way, if we do it like by writing equations blindly, the problem becomes mind-bogglingly complex and tedious. But if we do this, we have a fighting chance, and a very good chance. So here we have resistance of conduction of brick, resistance of conduction of stucco, resistance of conduction, resistance of convection inside. We said there is no heat transfer by radiation inside because everything is at the same temperature. Now you might say, so why do we have heat losses by convection? Aha, because I told you that the air inside is at 20 degrees and the wall actually ended up being at lower than that. Let me see what was the temperature of the wall. TS1, 11.6 degrees. So the wall, after we do the calculation, is more or less 11.6 degrees. So yes, there is heat transfer by convection from the wall to the fluid. But radiation is not between the wall and fluid. Radiation is between a wall and the other walls that happen to have the same temperature. And outside, we have this parallel circuit of radiation and convection that I can lump and turn it into something I'm going to call thermal resistance of the outside. That accounts for both things. Here we have, again, like the reciprocal is the sum of the reciprocals. This is what is embodied in this equation here. And we have, in the outside, we have convection and radiation, right? So before I put the numbers in here, what I wanted to suggest is that how to solve a thermal resistance problem. And in a thermal resistance problem, you might have something that looks like spider web, like this thing here. And you would not panic. What you would do is follow these steps one by one and say, okay, step one was find the parallel resistors, like here. These parallel resistors, turn them into an equivalent resistor, that is this case here. Step number two, find all the series resistors. Boom. I sum all of these, and we're good. And if you still have parallel mixed with series, mixed with parallel again, you keep going until you end up with a single equivalent resistor. In this case, it's very easy. I get this parallel circuit, and I move to here. Then I get this series circuit, and I'm done. This was a very simple problem, despite that started looking like a spider web. That's the point of this class. That's the point of this class, that these things that look complex, we can deal with. So let's look at resistance of the outside that accounted for convection and radiation. Convection, we already said, 100 watts per meter square Kelvin. So the resistance is 1 over that, 0.01. And for radiation is 1 over H rad. And H radiation had this expression here. And this expression is a killer because we needed the temperature of the wall. You see, it says, oh, here is a typo. It says T infinity. That's a typo. This should be T surface 2 and T surface 2 in here. But I don't know T surface 2. It's part of what I need to do. So in truth, this would be an iterative problem, but not really. We don't know what this T surface 2 is. But let's start by posing something that is not so bad. I knew that the temperature before was more or less similar to T infinity, right? Because I knew T infinity was, the convection coefficient outside was very intense. So the surface of the wall was more or less at the same temperature of the fluid, of the air outside. So if I assume that temperature, that is what we put here, we can calculate an H radiation that is approximate because I don't know the exact value of the temperature of the wall. And it gives us 0.2424. Look, the resistance of radiation, 0.2424, is a lot bigger than the resistance to convection. In a parallel circuit, that means that the small resistance dominates, which means the convection dominates, and radiation is almost as if it was not there, right? So I do the sum of the reciprocals, that I end up with something that is so close that 0.01, right? 0.09, 0.096, even closer. So what is the effect of radiation in this particular problem? It is very secondary. Inside doesn't matter because there is no temperature difference for radiation inside. And outside, the circuit is parallel and the resistance to radiation is so much bigger than resistance to convection. So convection wins in this case. All the heat goes by convection and whatever goes by radiation is very small. When I put all this together, right, now this problem that is done as accurate as we could for one wall, we get this total resistance that accounts for brick, stucco, convection inside, convection outside, whether the air is stagnant or the air is forced by the wind, radiation inside and radiation outside. What else do we ever want, right? And what we see is that because many of these factors were secondary factors, the value we get is more or less the same as before. To give you an idea, when we calculated the wall, accounting for convection, we got 3.587. And now we got 0.3583. The difference is little and is in the fourth digit. But we can do it if we want. And if all of a sudden the house is glowing red hot, well, radiation might become relevant, and we know how to account for that. And what we did is very simple arithmetics. Would be a pain to do any other way. But we engineers know this. Physicists don't. Physicists see this and say, oh, that sounds kind of smart. Yeah, of course it's smart. But physicists don't build cars and planes and power plants, and we do, right? So we need to be smart in using these laws of nature. Now, we were talking about a wall. So let's talk about a real house that has walls over the place. So let's talk about a simple case, which I'm just going to make the circuit. We have the temperature inside your house, and you have the temperature outside the house. And here you have the heat is going in parallel ways simultaneously through wall 1, wall 2, wall 3, wall 4, leaving through the roof. So you have this parallel circuit in which each of these walls has convection, radiation, conduction through many separate layers. If you want to do a fine calculation for your house, now you can, you're ready. And I'll teach you more because many of these values are even tabulated. A funny thing, if you want to calculate the overall resistance, thermal resistance of your house, is actually a lot simpler. You look at the average temperature outside for a month, you look at the average temperature inside for that month, and you have a delta T. You look at your bill for heating, and you know how many gigajoules you put there in a month. You do the delta T divided the amount of heat you know you burned, and that's the thermal resistance of your house. Now, that's the easy part, right? And knowing that thermal resistance, you can infer what would happen, how much you would pay if the weather changed. This is pretty cool. You can infer how much, what size of AC you would need if you care about putting an AC in your house. and all that just with the concept of thermal resistance. If you wanted to see what is the effect of having more windows in your house, you can do it. Super awesome. Okay, I'm going to show you later how many of these things are all bundled together. One more thing, one of the heat transfer mechanisms we studied was thermal resistance of contact, which is very similar to convection in its mathematics in the formula. And if you remember, we had an H for contact, right? That had a formula very similar to convection, and the thermal resistance of contact is 1 over this H of contact. Very simple. But now that this enables us to account for, to use the concept of contact resistance, even when we don't have convection or radiation, but just contact between two solids. We can do so much now. And we can have a solid that has paint and is in contact with other solid that has paint, and now we would have thermal resistance of a solid, thermal resistance of the paint, thermal resistance of contact. You told me what you want to account for, and now we can. This is awesome. So now that we know all these concepts of thermal resistance and how we can combine them, I want to introduce the concept of overall heat transfer coefficient, which is essential for heat exchangers. And by the way, when you buy windows, you also get that, right? So what is this overall heat transfer coefficient? We said that the amount of heat that goes through a system, such as a wall or a window, is delta T over the thermal resistance. Or we can pick a reference area. For the case of the wall, it's very simple because the area for heat transfer is the same all the time. But in some cases, as we're going to see next week, you can have something like a cylinder in which the concept of thermal resistance also applies, except that inside you have a small diameter, so you have a small surface, and outside you can have a big diameter because you have a big surface. Yeah, you have a big surface. So you pick you can pick the area inside, you can pick the area outside, you can pick any area you want, but you have to say what it is. You must specify what this reference area is. Now, once you specify the reference area, this 1 over R double prime, that has a name, U, and is the overall heat transfer coefficient. This value of U, for example, is tabulated in chemical engineering handbooks for different types of heat exchangers. In this class, we're going to learn how to calculate U for pretty much any type of heat exchanger. But if you just want a ballpark value, those values of U that you are going to learn to calculate are also already given for general cases in chemie books, handbooks. So for the case of our wall, the overall heat transfer coefficient would be this one, U, 1 over R total, 2.791. The units of the overall heat transfer coefficient are the same units of the convection coefficient, watts per meter square Kelvin. And in reality, this is kind of like a generalized convection coefficient. Is if you had only convection, U equals H. But if you have convection and conduction and radiation, blah, 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 all those together, like you get the total resistance per unit area, you flip it in the reciprocal, and that becomes U, which is tabulated. We have 10 minutes, and I want to introduce a concept which we're going to be using a lot. And this is something I love. And of course, it's not in the book, but it's the concept of boundary layer. You already heard the term boundary layer in fluid mechanics, and I already used this term. I think was earlier this on Monday, very loosely, and I'm still going to be using it loosely. But I want to start to discuss an important aspect of convection, which we're going to see a few weeks down the line. But I want to introduce some key ideas. The heat loss by convection, right, that has this formula H times delta T, sounds almost like magical. But this is the reality. Convection, as we mentioned in the second week of class, when we talked about heat transfer mechanisms, convection is a combination of advection and conduction. So convection can only happen when we have a fluid in motion, right? That's the advection part. What is the conduction part? Is that the fluid in motion creates a boundary layer, like you saw in fluid mechanics. And through that boundary layer, you have conduction. So in reality, convection is nothing but conduction through this boundary layer. To give you an idea, I am here in front of the camera, and my hand is more or less 33 degrees. The skin of my hand is at 33 degrees. The air is more or less 20 degrees. So there are some currents of air going up because of the warm air coming from my hand. This motion of air is creating a boundary layer. And the heat losses from my hand into this air are in reality, we call it convection, but in reality is conduction through this boundary layer. And why am I introducing this now, and why I insist so much with this? Well, the reason I insist is because everything we're going to see about convection, and we're going to see some crazy empirical formulas, they all make sense when you understand this concept that convection is nothing but conduction through a boundary layer. The other thing is, okay, whatever, we have conduction through a boundary layer. I'm going to ask now, how thick is the boundary layer? And believe it or not, right now, together, we can calculate the thickness of this boundary layer. And I think it's an amazing thing. So here we have a person that is warm, and the air goes up, right? Just like you see the hot air rising from a bonfire. And this is the way we're going to calculate the thickness of this boundary layer. The heat I'm losing by convection, right, can be calculated. See, if we see heat per unit area, heat flux, right, would have a thermal resistance that is given by 1 over H. That's the thermal resistance of convection, 1 over H. And we know that ballpark for natural convection, 1 over H in air, 1 over H is 10, and natural convection in forced convection in air is more or less 100. So we know that about H, and we know that the thermal resistance of convection is 1 over H. Now, what I'm saying, in reality, this 1 over H, which is convection, in reality is conduction through a layer of air. The amount of heat going through that layer of air, of course, is the amount of heat of what we call convection. And we know the thermal resistance of this layer of air is going to be given by L over K. This is the thermal resistance of a wall. What I'm saying is that what we call convection in reality is this thin wall of air surrounding us, thin wall of stagnant air. We're going to see that in a lot more detail later in the convection unit. But let's start by acknowledging we have a boundary layer. So I know that the thermal resistance of this thin wall of air is L over K, which we also call convection, which has thermal resistance of 1 over H. Is the same thing. Same thing. From here, I can solve for the thickness of this boundary layer as K over H. The K is thermal conductivity, and the thermal conductivity of air is 0.03 watts per meter Kelvin, give or take. That's depends on the temperature, but that's a good number at 20 degrees. And so I know this, and I know these 10 watts per meter square Kelvin or 100 watts per meter square Kelvin for air. So if I'm I'm sitting like this guy here, the thickness of the boundary layer would be 0.03 watts per meter Kelvin divided 10 watts per meter square Kelvin, and that gives me 3 millimeters. You don't see it, but around me and around you right at this moment, there is a more or less 3 millimeter layer of quiet air surrounding you. And the reason you don't feel too hot and you don't feel too cold is because that thermal resistance is taking all your metabolic heat, and the heat of thinking is taking it away through that layer. If the layer was thinner, you would feel colder. You're losing more heat than you wanted. If the layer was thicker, you'd feel hot. Now, if there was wind, that would be forced convection, and the thickness of this boundary layer would be 10 times smaller, 0.3 millimeters. Now it's easier to see why on a windy, if it is cold, wind makes things worse. Because if it is cold, but the air is still, I have a 3 millimeter layer of air protecting me. So I have clothes. But if you don't have clothes, you still have a layer that is protecting you from losing all the heat, this boundary layer, right? And if you increase the velocity of the air and you force it, all of a sudden this layer of air that is protecting you is 10 times thinner. So to some extent, you have an invisible jacket that wind makes very thin. So this is a pretty cool thing. We understand now exactly what's going on and why wind makes things feel colder, because the temperature of the air is the same with or without wind, but the feeling is very different. So we can look at water too, and the thermal conductivity of water is 0.6 watt per meter Kelvin. And we do the same calculation because we know that natural convection in liquids, in water, is more or less 100 for natural convection and 1000 for forced convection. So we do the same calculation and we get a very similar result. That if you're just sitting in a pool, that's okay. You have a boundary layer of about 6 millimeters. But if you start swimming, you have a boundary layer of water that is about 0.6 millimeters. And you have a double problem, right? Because the boundary layer is very thin when you're swimming. And in addition, the water is quite conductive. We don't have this protective layer of air keeping us warm when we're in the water. So I think this is a really good illustration of how this concept of thermal resistance is helping us understand something that is not very obvious, and the book doesn't make obvious. And it is, what is convection? What does it mean? And now we know that convection is conduction through the boundary layer. And our whole problem when we get into the units of convection, we're going to see convection for 3 weeks, is all going to be, okay, what is the thickness of that boundary layer? Because it's the thickness of the layer of insulation. And we can start anticipating it now. I think it's quite awesome. So right, is 1:50. And on that note, I wish everybody a very restful reading week. I'll be back at 2 for office hours, and I hope many of you will want to join me. Thank you very much. I'll see you later.